Maximising optical fibre capacity. The total amount of fibre optic cable is in excess of 800,000 kilometres, and these fibres carry 99% of the world's data. Consumer demands for data have risen dramatically over the last decade, and is projected to increase at an even faster rate. Cheaper bit rates cause an increase in users, further creating more demand for even cheaper bit rates. A positive feedback loop. Total internet users in 2010 were 2 billion, and in 2015 rose to 3.2 billion. Long-haul fibre optic networks are cables laid on the seabed, carrying data intercontinentally, and are key to the world's fibre optic telecommunications infrastructure. These long-haul cables transfer around 38,000 petabytes per month in 2016. Calculations suggest that to keep up with the increase in total global data usage, long-haul traffic must be approximately doubled and reach 59,000 petabytes per month in 2019. A tempting solution would be to simply install additional fibre optic cables. However, this is not a feasible strategy. Even if optical fibres are added with existing technology, because the cost and capacity of the cables remains the same, the cost per bit does not decrease. The TAT14 is a typical transatlantic fibre that stretches over 15,000 kilometres. It uses a multiplexer to combine multiple channels of information at the transmitter end, and a demultiplexer to separate them again at the receiver end, operating at a capacity of 1.87 terabits per second with a maximum possible capacity of 3.2 terabits per second. Current commercial technology such as the TAT14 uses channels with 200 gigabits per second and up to 16 channels to create a maximum total system bit rate of 3.2 terabits per second. Because the total internet traffic will approximately double by 2019, a per system capacity of approximately 6.4 terabits per second is needed with an excess of 4 terabits per second needed to compensate for anomalous rises in usage, the total needed capacity being approximately 10 terabits per second. The Unlock program at UCL achieved an experimental transfer rate of 1.1 terabits per second, making augmentations to only the transmission and reception methods while using a single channel over a standard single-mode fibre. The maximum experimental transfer rate is called Shannon's capacity, which depends on the Shannon's theorem. The theorem states that the maximum limit will increase if the signal-to-noise power ratio increases. This will be achieved by decreasing the noise in the system. This was done by improving signal-to-noise ratio and encoding signals using techniques previously only used for wireless technology. In a 16-channel system using this augmentation, the transfer rate would be 18 terabits per second, exceeding the goal of 10 terabits per second. However, this was achieved with short-haul intrametropolitan, not long-haul. This projection assumes the same transfer rate applies to long-haul, or that power loss in the cable over distance is less than 50%, which still allows the 10 terabit per second goal to be met. Due to greater transmission rates, there will be greater competition in the telecommunications market, rendering the current bandwidth amount cheaper for front-end, namely household users, the new, higher download speed becoming a premium bandwidth, and the old bandwidth being still available as an economy option. Unlock uses contemporary, non-experimental, single-mode fibres, meaning it is compatible with current systems and economically viable for long haul. As the results were achieved with a point-to-point system, upgrading the current systems would only require the replacement of start and end nodes, minimizing upgrade costs. Our conclusion: therefore, if our assumptions hold true, applying Unlock's research will meet the increasing demand for an increased capacity in optical fibres.